Alright, so Physics 12, this is our lesson now on equilibrium. So last lesson we were looking at torque, and in this lesson we'll be combining what we just kind of learned about torque and bringing it in with a concept of equilibrium. Okay, so here we go. Alright, so you might already be familiar with kind of the concept of equilibrium in the sense that, if you have all the forces acting on an object being equal but opposite, you essentially get no overall motion, and you're considered in equilibrium. And what we discussed last lesson with the idea of torque is that you could have equal but opposing forces on an object and still be moving, but moving in a rotational sense, right? And that's where that idea of torque comes into play. So when we talk about equilibrium, since there's now two types of motion, right, translational motion and rotational motion, we can also talk about two types of equilibrium, right? So translational equilibrium and rotational equilibrium. So with translational equilibrium, like I mentioned, was when the sum of all of your forces that would cause translational motion, right, so just kind of like motion in a plane, when all of those forces are zero, you have equilibrium. Okay? With rotational equilibrium, that occurs when the sum of all the rotational forces are zero, and rotational motion forces were what we used as torque. Okay? So again, if the sum of all of your forces acting on an object are zero, then you're in translational equilibrium. If the sum of all of your torques are zero, then you're in rotational equilibrium. Okay? And then if you're in static equilibrium, right, you actually get both. So if the vector sum of all the forces acting is zero and the sum of all the torques is zero, right, so you kind of see there, right, the sum of your forces is equal to zero and the sum of your torques is equal to zero, then we can say that that object or that scenario is in static equilibrium. Okay. Now again, what we're noting here is that a useful feature with torque is that if an object is in static equilibrium, right, then the sum of the torques around any pivot point is zero. Okay, so what that means is as we go through a problem, we can decide what point we want to be as the pivot point. Okay, and just kind of by looking at what forces are being acted on objects at different points, we might be able to say, well, wait a minute, if we choose this as a pivot point, it gives us a better value of some of our torques being zero, and we don't have to do so much calculations, versus choosing another pivot point where you actually have to do more work. Right, so just kind of keep that in mind as we go through these problems, all right? And I'll give you the fair warning, these problems can get lengthy because there's so much to analyze with each one, all right? But we'll just kind of try and take our time and get through them as much as we can, okay? Now, some things to keep in mind when we're solving these types of problems, okay? There's going to be a lot of things going on, so you're better off making sure you're assigning symbols for each force that's going to be used, right? You're better off having everything well labeled. Excuse me, than not, or else things are just going to get really confusing, right, when you're trying to look at all these different values. Okay, so correctly label things. When you're looking at trying to set up your forces, right, you'll need to look at them in, again, two dimensions, right, so look at them in terms of their vector components, right, what are all the sum of the forces acting on the y-axis, what's the sum of the forces acting on the x-axis, right, and you'd want to be able to set those acting on the y equal to 0, and the ones on the x equal to 0, and then also setting all of your relevant torques equal to 0, okay, so this might be used to help find a missing but relevant force, right, because remember your torque is equal to that length of your lever arm multiplied by a force, which might be able to, if you have the length of the lever arm and you know what that missing torque value is supposed to be, it can help you actually find the missing force value if it wasn't able to be found in one of these two steps here, okay? Now, other than kind of this first one where it's assigning the symbols, these can be done in any order, right? You don't have to start with the ones with the y and then go to torque and then go to x, right? You could do x and y first and then go to torque. You could try to do torque first and then switch them up. Sometimes you don't even need all of them, right? Sometimes you may only need the torque equation. You don't need the ones with the forces, right? It depends on the question, right? But again, you'll notice that these problems will involve at least one of these steps. So just kind of thinking of those things, right? So looking at your diagram, identifying, okay, what are all the possible forces that are acting on this particular, on this particular object or in this particular situation, and then from there, that means you have, for every force, there's a relevant torque, okay? So we'll kind of go from there, Okay. Again, just kind of going back and reminding us of some key points from our lesson on torque, right? If you're being asked to find the weight of your object or the force of gravity acting on a particular object, you have to do it from the center of its, like center of the mass, essentially. So if it's a length of something, you need to do it as half the length, right? And then that would be the length of the lever arm. Okay, so make sure you're using that value. And also remember that gravity and normal force occur in opposing directions, right? So one will be positive, one will be negative. Typically, you get gravity as obviously your negative, but also don't forget that if something's leaning up against a wall, normal force isn't always just going up, right? If your object is resting against something, against a vertical plane, right? So say, and it's going to come up in this first example, we're going to do a ladder leaning up against the side of a house. Well, it's resting on a vertical object, which means the normal force is actually acting out, right? Out of the wall. So just kind of don't forget little things like that, right? Because by definition, normal force is something that's that acts perpendicular to the object at which it's resting, not necessarily just opposite gravity. Okay, it just so happens when things are lying on a flat horizontal surface, normal force does happen to be opposite gravity. Okay. So let's go through these. Unfortunately, again, with my small little whiteboard, it's going to be a series of erasing with the amount of stuff we have to solve here, but let's kind of go through it as best as we can. So here's our situation. We have a firefighter that stands 2/3 of the distance up a 4.0 meter ladder. The ladder has a mass of 35 kilograms and it's leaning against a burning house. Assume that the friction between the ladder and the side of the house is negligible, right? So we're assuming that there's no friction occurring here with the interaction between these two objects, okay? The total mass of the firefighter and the gear that they're wearing is 95 kilograms. We know that the ladder makes a 58-degree angle with the ground, and it's asking what must be the coefficient of static friction between the ladder and the ground to prevent the ladder from sliding backwards, right? So we basically need to know, all right, that force of friction, right, that would be this way here. What is that so that it doesn't go this way, right? What force being applied in this direction will prevent this slide out from happening, okay? So let's get started with some key things here. All right. All right, so if we're going to kind of redraw that, and we'll just kind of do it as some, main steps here. Here's something that's representing our ladder, okay? Now, you've got the firefighter standing about 2/3 up, okay? And what's going to happen is that gravity is going to pull that straight down, okay? You've also got the mass of the ladder, and the center of mass would be about here, and that's going to be pulled down as well, right? Not as much as the firefighter because its mass is less. We also have the fact that force of friction, this is what we're trying to find, is pulling in this direction. Okay, so I'm going to call that force of friction. This would be normal force, right? Because again, this is resting on the ground, right? So it's resting on a horizontal surface, so the normal force would be here, and we'll call that the normal force of the ground. Okay, and then what we have here is, again, this is resting against a building here, so the normal force here is actually going to act out in this way, right? But we're assuming that the friction is negligible here, so nothing is happening in this scenario, okay? So that's the only force that's being applied here. So this is the normal force of the house, okay? And we'll call this the weight, so force of gravity of the firefighter. And then this is our force of gravity of the ladder. Okay, so again, we're going to indicate all of those things, right? So if we wanted to be very, very clear, we're saying, okay, so F and H, that's normal force of the house, the building. We have FG, FF, right? So that's our weight, so like force of gravity acting on the firefighter, right? So weight of firefighter, and then FGL, so that's our force of gravity acting on the ladder, so that's essentially just the weight of the ladder. Okay, this is our force of friction on the ground. Alright, so force of friction on the ground. And then finally we have our normal force here on the ground as well. Okay, so these are all of our forces that we have happening. Okay, so again, what we're trying to do with this equilibrium, right, because we're assuming that we want all of this to stay, right? We don't want the ladder to be sliding, we don't want it to be rotating this way, right? We don't want it moving right or left, we don't want it moving, rotating up or down, right? So we need equilibrium to be in play here, right? So we need to make sure that the sum of all of our forces in the y direction are adding up to 0. We need to make sure the sum of all of our forces acting in the x direction would be equal to 0, and we need to make sure that the sum of all of our torques are also going to be equal to 0. Okay, so in this case, let's start off with our y values. Okay, so what we're actually looking for here is the sum of our forces in the y being equal to 0. Okay, I'm just going to erase this section now so I have some more work, but I'll leave our diagram so we can keep looking at it. Okay. So we're going to start off with that. So we're going to talk about, we want the sum of the forces in the y being equal to 0. So let's analyze what forces do we have actually happening in the y direction. Well, we have our normal force from the ground, we have the weight of the ladder, and we have the weight of the firefighter. These are the only forces in the y direction, right? This one is acting positively, and these two are acting negatively, right? So essentially what we have is this positive normal force to the ground minus our weight of the ladder minus our weight of the firefighter, all equal to 0, okay? So these values we can actually solve quite easily, right? Because, well, what we have is that we know the weight of the ladder, right? The mass of the ladder was given to us as 35 kilograms. We also know the mass of the firefighter, which is the 95 kilograms, okay? And then we can obviously just, assuming that we're on Earth, we can multiply that by our 9.81, okay? So what we can do here is say, well, okay, well, the normal force here, which we wouldn't have, right, because we don't have any other information to solve this, right? We don't have the force of friction, we don't have the coefficient of friction, so solving needs to be had. But we can find this just by bringing these over to the other side, right? So our normal force to the ground will actually equal the sum of the weight of the ladder and the weight of the firefighter, right? And again, that's just going to be mass times gravity, right? So normal force here, so the ladder was 35 kilograms multiplied by our 9.81 meters per second squared. And I'm having this as positive because I assumed it was negative over here, so we're good there, right? Plus our 95 kilograms multiplied by our 9.81 meters per second squared, okay? So in doing that, what we get are two different values, right? This ends up being 343.35 newtons. This ends up being 931.95 newtons, and when we add them together, we get a value of 1,275.3 newtons, and then that's positive because it's acting in the upwards direction. Okay, so there's one thing checked off the list. Okay, now another thing that we're going to be able to do is look at the sum of the torques. Okay, so the sum of all of our torques is going to enable us to find what that force of friction, some of our torques is going to be able to find out what this normal force of the house is going to be able to give us, okay, which will then enable us to be able to set up our sum of things in the x, right? Because just as an example, if we were trying to do sum of the forces in the y, and then you thought, well, why am I going to go to torques? Why don't I just go the sum of the forces in the x? Well, if we did that, right, and we said, okay, the sum of the forces in the x is equal to 0. Well, that means that this force of friction down here, and then minus this force normal of the house, is equal to 0. Don't have this. You're like, oh, well, I know how to find it. It's just the coefficient of friction multiplied by the normal force, and I have the normal force. but wait a minute, we were being asked to find what is the coefficient of friction. So I don't have the coefficient of friction, I don't have the force of friction, so I can't find anything here. Okay, well, can I find out what the force of friction would be just from this? Well, that would require more information of what's happening here, and I don't have anything else that's happening there, right? The weight of our ladder is here, not here, right? So this is not helpful at this stage. We will get to this, but what we can do is we can figure this out using our torques, right? Because the sum of the torque, we have to use all the forces. We need to find the torque on all of the forces acting on this object in order to figure out, that all of those sums has to be equal to 0 for it to be in equilibrium. Okay, so our next stage is, we'll leave this, right? We've got to come back to this, but we now need to look at the sum of our torques. Okay, all right. So again, we need to look at every single one of these things and having the torque of each of them. Okay, now if you want, you can, break it down really, really slowly and look at, okay, well, what's happening at each of them, right? Like, what's the torque happening here at the ladder? But before we even do that, we need to decide, well, what's going to be our pivot point? What do we want to decide to be as the pivot point, right? And again, we can choose it based on anywhere, and it makes the most sense to actually choose this spot right here. Reason being is that if this is the pivot point, then the torque of both of these forces is going to end up being 0 because the distance that these forces are away from the pivot point is 0. Okay, so that kind of helps us with two things. If we chose here, it only affects 1. If we chose here or here, again, it only affects 1 being to 0. So we can choose our pivot point here. So let's take a look maybe at torque of the ladder. All right, so our torque of our ladder, remember that this was at an angle of 58 degrees. From our lesson on torque, torque is equal to the perpendicular distance, right, of the force, the lever arm. Okay, so that's the perpendicular distance of the ladder, multiplied by the force, right? Well, we have that value, right? We can just get it from your mass times your force of gravity, okay? And in order to figure out, well, what is that perpendicular distance, we basically need to find, right, if we were redrawing this, I guess, just going to the ladder, right? There's your 58 degrees. This is your force acting down, so I need this to be a right angle, and I'm interested in this distance right here. Okay, now because we did this as half, right, exactly half the length of the ladder, which was 4 meters, this value would be 2 meters, which means this value would be found using your basic right angle trig. It's the adjacent side, so this would be found by using cosine of 58 degrees multiplied by your force of gravity of the ladder. Okay, and force of gravity of the ladder, like I said, would just have been the 35 kilograms multiplied by your 9.81. So the torque of our ladder ends up equaling, where did I write that down? Okay, sorry, I made a mistake here. This is cos of 58 degrees multiplied by 2 meters to get the actual length, and then you're multiplying it by the force of gravity, which would be your 35 kilograms times your 9.81 meters per second squared. Okay, and that would end up actually being a value that's negative because we're pulling down. Okay, so doing all that, your cos of 58 times 2, that gives you this value here at 1.06 meters, and then you can multiply by your force of gravity, and that gives you a torque of negative 363.9 Newton meters. Okay, so there's the torque of our ladder. We do the same thing for the torque of the firefighter, right? So there's one thing. We need the torque of the firefighter. Okay, so again, that's going to be that perpendicular length, right, to the force, multiplied by the force of the weight of the firefighter. Okay, so again, in this case, we're looking at kind of like this triangle, right? There's our perpendicular line. This length here, right, that was 2/3, right? The firefighter was 2/3 up the ladder, so that ends up being like 2.67 meters, or 2.666 repeating, or 8/3 if you wanted to be as exact as possible. And once again, we're interested in what is this distance, and again, it would be that same right angle triangle, cosine of 58 degrees, because it's the adjacent side length. Right, so the torque of our firefighter will equal that cosine of 58 degrees, this time multiplied by that 2.67 meters, and then multiplied by that force of gravity of the firefighter, which was the 95 kilograms, multiplied by the negative 9.81 meters per second squared. Okay, and we do all of that, and we get that the torque of the firefighter ends up equaling a value of negative 1316.85 Newton meters. Okay. All right. So again, I mean, the negative positive part is really coming from that right-hand rule again, right, where you're placing your, hand on the paper, and you're looking at, okay, this is where, this force is acting, right, my lever arm, and then I'm rotating, right, this way, right, with the force, right, and when I do that, I'm going into the page, so therefore it's the negative, right, it's the clockwise aspect, okay, but anyway, we can identify that as negative. Okay, so now we got to look for torques of some other things. So we have torque of the ladder, torque of the firefighter. Like I said, we can't quite calculate this torque, right, because we don't have any information about it, right, other than, okay, well, I guess the distance from the pivot point would in fact be 4 meters there, okay. So let's see what else we can do. But we do know that this torque would end up being 0, right, because its distance, right, the force is acting here. What's its distance of the lever arm, distance from the pivot point? That's 0. Same with the force of friction, right? So if we kind of like talk, okay, well, what's the torque of our normal force to the ground? It'll be 0, right? What's the torque of our force of friction? Also 0, right? Because again, its distance from the pivot point is 0, which leaves us to being able to say, well, if I can do the sum of all of the torques, then this one, right, I can find the torque of this quite easily. Okay, so let's go and do that. Okay, I'm going to start erasing this diagram now because I think we're mostly good. I'll redraw it again if I need to. Again, these are lengthy, but we'll get through them. Okay, so what we're saying here is that the sum of our torques, right, need to equal 0 to be in that static equilibrium. So what that's saying is, right, all of these values, right, plus the other torque of the normal force at the house need to equal 0, right? So it's like that. Oh, I'm going to have to erase all of this. I need the space. Okay, so that means that the torque that was normal to the ground plus the torque of the force of friction plus the torque from the force of gravity on the ladder, plus the torque from the force of gravity on the firefighter, plus the torque on the normal force of the house, all has to equal 0, right? And you'll recall we had values for this, and we can solve for that one, right? So what we're saying there then is, okay, fine. Then this, the torque for the force that's normal to the house, right, is going to end up equaling, you can bring all these over to the other side, and it's negative torque of that one, minus the torque of that one, minus the torque of that one, minus the torque of that one. Firefighter. Okay, so this was 0. This was 0. This was a negative 363, so you're subtracting a negative, so it would turn into a positive Newton meters. Again, subtracting a negative again, and that had a value of 1316.85 Newton meters. And remember that our formula for torque is, in fact, the length of the lever arm, right, multiplied by the force, right? So this is the lever arm, right, that's perpendicular to the force, and that ends up equaling a value of 1680.75 Newton meters. Now, this is ultimately what we want, right, because then we can go back and find the force of friction, and then what we'll do is divide it by this. And like I said, we could find this if we kind of reconsider that diagram here. This was the normal force, right? normal force of the house here, acting out in that direction, we know that this ladder has a length of 4 meters, and what's going to be perpendicular to that force is this value here, right? And that would be found by using the sine, right? Because again, this is our 58 degrees, so what we're looking for is the opposite side length. This is going to be our, right, because that's our pivot point, perpendicular. That would be our perpendicular length, right? So that's the opposite side length, so we're going to need sine of 58 times 4, right? So this is now F and H is equal to the 1680.75 Newton meters divided by the sine of 58 degrees multiplied by 4.0 meters. And then when you do that, you get that the normal force of the house is equal to 495.5 newtons. Okay, that now finally allows us to figure out what that force of friction is, because we can go again and talk about the sum of the forces in the X. Okay, so, alright, so now I need the sum of the forces acting in the X are equal to 0. Again, from our kind of basic diagram, right, there was one going down, this one was also going down, right, this was going out, this was going out, this was going up. So the only forces actually acting in the X here are this one, our force of friction, and our normal force to the house. So the sum of these two things need to equal 0. Okay, now if we're thinking about this, force of friction is acting in a positive, normal force is acting in a negative. What I can do is just figure out what my force of friction is, subtracting this value, but it would be subtracting a negative, right? Because this value we had just found, that normal force would end up being, was the 495.5, right? So in order for these two things, right, to be equal to each other, right, or for to equal 0, sorry, they have to equal each other, right, like in the opposite direction, right? So if I give that a negative value and I interpret this as being positive, right, that force of friction, that means that our force of friction will also need to equal that same value of the 495.5, right? And I guess I really should have identified this as being a negative in this case because of the direction pulling to the left, okay, if that's how I wanted to identify it, right? So there's my force of friction. And now I can finally find my coefficient of friction, seeing as my force of friction is equal to the coefficient of friction multiplied by that normal force, and at that main point, right, that's the normal force of the ground, which we also have a value for. So force of friction divided by that normal force on the ground will equal my coefficient of friction. So I can take that 495.5 newtons and divide it by that normal force for the ground, which we solved way back when we did the sum of the forces in the Y, which was 1275.3, right? And that actually gives us a value of 0.39. Okay, so this is the coefficient of static friction that we need to maintain equilibrium. So, as you can see, these can take a while. Now, they won't take as long as what I just did, simply because you're not going to be explaining it the whole time, right? You're just kind of writing it down and figuring it out, and it won't take as long, okay? But that's, you know, the gist. Now, again, that was probably the most complicated one, where you needed to do all the sums of the torques, and you needed to do all of the forces in the X and all the forces in the Y, right? Some of them are less complicated. You don't need to do as much work, but they're still tricky enough. So already this video is like a half hour long, and we've just talked about what this is, and I did one question. I'm going to pause it, like I'm going to stop this video, I'm going to upload it as it is, but then I'll make a second video that will just go over some of the other examples. Okay, so I'll post, the notes are already posted, I'll post this video. If you think that's enough for you to go, yeah, I'm good, I'm just going to go and do the other questions, the answers are still in the slide, so you can kind of look and see if you're doing it right there, but I will also post the video with the other So 3 other sample problems, just so if you do want to see and hear me explaining what I'm doing in each of the steps, that's good as well, right? But if you're feeling this one example is good enough, I think I'm good with this and then the slides, that's fine. That other video can just be a, maybe I will watch it if I am really stuck and I don't understand, okay? So that's the plan. So if you want, you can try the other sample problems, right? So this was, as you can see, there's 3 slides that need to be done for that, right? There's a second problem here. And again, you get like a bunch of things. You've got a third problem there, and then you've got a fourth, okay? So they're all there. You can try those other sample problems, but again, I will do those as full. I'll do them as a video now again, but just as a separate video, okay? And then there's also worksheets, and again, these worksheets, worksheet number 1 is sufficient if you're just looking for extra practice. That's where worksheet number 2 can come into play, right? Because as you can see, these are lengthy. If you feel like you've got the hang of it, just after a few of the questions, like from worksheet number 1, that's fine. If you want more practice, go for worksheet number 2, because as you can see, just doing 3 problems is going to take a while, okay? So if you want to watch the next video, go for it. If you think you're good, just maybe go through the sample problems yourself and go straight to the worksheets. All right.